All right, let's get started. My name is Dan Simmons. I'm the director of the Natural Resources Task Force of the American Legislative Exchange Council. It's an organization of state legislators. Part of my task is, well, to keep our state legislators informed of the issues of the day. Natural resources means a lot of discussion about energy, and hence we've had Joe DeLeo come and talk to our group before, and I look forward to hearing Art and John's presentations as well. We're going to start with Joe DeLeo. He has more than 3 decades of experience as a meteorologist and climatologist. He is currently executive director of ICCC, an organization and website devoted to climate change issues. That website is icecap.us. I highly recommend it. I read it almost every day. He is a professor of meteorology for 6 years. He was a professor of meteorology wow, I've lost my ability to speak. He is the professor of meteorology for 6 years at Lyndon State College in Vermont, and from 1981 to 88, he was the first director of meteorology at the cable TV Weather Channel. Please join with me in welcoming Joe DeLeo.
Well, I am not a denier of change. The only constant in nature is change, for sure. Today we will look at station data, and my presentation is slightly modified from the version you have there, since Ross did such a good job with the station data yesterday or this morning. I've added more on the ocean, but I will look briefly at the global databases and talk about how they have major issues and why I chose to work with the U.S. climate stations. I'll correlate temperatures from the U.S. data with the carbon dioxide, solar, and oceanic cycles and show how they correlate better than carbon dioxide with the temperature, and that there's a similar story in the Arctic and Greenland. This is the NASA GIS global temperatures since 1880. Pat Michaels presented yesterday. Certainly looks like we have a problem there in accelerated warming, 2-phase warming. But there are issues with the global station data. There's this big station dropout that Ross talked about. We went from 6,000 to 2,000, most of them after 1990. At the same time, there was a large increase in the missing monthly data. There's little or no or improper urbanization, urban adjustment being made in the global data. And there are alarming issues that Anthony Watts and Pielke and others have identified with the siting of instruments and land use changes, all which produce a warm bias. And there's numerous peer-reviewed papers ignored by the IPCC and media that estimate that these problems in the observing networks could account for 30% or 50% or more of the warming since 1880. The National Climate Data Center that Ross mentioned has 1,221 stations, and they make adjustments for time of observation, missing data, type of instrumentation, siting, and urban warming, at least in version 1. Version 2 in 2008 eliminated the urban adjustment, replacing it with a new algorithm, a change point detection algorithm. This is the USHCN version 2 temperature plot for the U.S., the 1,221 stations going back to 1895. You see less warming, and you see a cyclical change. Now, the change between version 1 and version 2 is a little hard to explain. You see warming in version 2 in the early part of the century up to about 1930s. That red line should be up at 0. Actually, a little cooling in the 30s, 40s, and 50s, and then warming, especially after the middle 1990s. These have the effect of producing a little bit more of a hockey stick look to the U.S. Temperature data, if I was cynical, which of course I'm not. Let's look at that temperature relative to the CO2 data. This is using the CDIC data going back. I'm on a lower since 57. Before that, the ice core. Of course, Beck would argue that there is actually a spike in the CO2 in 1940 as degassing occurred after the warming that we saw early in the century. But let's go with this. And we did a correlation of the CO2 with the temperature, and we found an R square of 0.4, a fair correlation. Now, in the last decade, that correlation disappeared. The Pearson coefficient is minus 0.14, and the R squared was 0.02. Now, some of that may be the result of the 1998 warm spike, and we'll look at that in a second. I also then said, well, how about the global database? And so I took the monthly Hadley temperatures and the monthly MSU satellite temperatures and plotted that and did a correlation with the CO2. And I found similarly very small correlations, 0.001 or 0.005 for the satellite. Okay, so if I'm Pat Michaels, I'm concerned about that early warming there, and it's not fair to use the full 10 years. If I start at 2000 at the base of the cold spell and go to the end, the correlation improves to 0.02, not very much. If we're told, as we're told by Gore and Hansen, it is far worse than even the most alarming climate models, the correlation should not be falling, should be rising, and 10 years is not enough, is enough time to see that. What kind of factors could be responsible then for cyclical change? Certainly the sun, we talked about the 11-year solar cycle. The 11-year solar cycles vary in strength on longer cycles, was mentioned, Tim Ball today, 88, 106, 429. You can see the 100-year cycle in this data. Each of the 11-year solar cycle varies in its strength, and the stronger it is, the warmer the result. You can see about every 100 years there's a quiet period, and leads to speculation about what's about to happen in the decades ahead. There's also a 200-year cycle, so if you go back to the early 1800s, that certainly was a cold period. We're going to be phased now with the 100 and 200-year cycle in the upcoming few decades. The solar connection has both direct effects, as Fred talked about, changes due to changes in brightness of the sun or radiance, relatively small in the 11-year cycle, 0.1%, but since the Little Ice Age, 0.45%. The indirect effect, though, magnified that. That's ultraviolet warming through ozone chemistry. That wasn't mentioned, I don't think, this morning, at least not in the lunch session. High up in low and mid latitudes, and we'll show you that in a second. They did talk about the geomagnetic solar wind effects that can warm high latitudes and reduce low clouds through the diffusion of cosmic rays. Now, Scafetta and West had two papers, the latest one in 2007, that suggested the total solar irradiance was a good proxy for the total solar effect, the direct and indirect, and it could account for 50% or more of the warming. I did a correlation with the USHCN, with the TSI that came from Hoyt, and I found a correlation of 0.57. So better than the CO2. You see a better match. I didn't do a lag of temperature to solar, which probably would have increased the R squared some. Now, ultraviolet increases, as Tim Ball mentioned, although solar irradiance only changes 0.1%, ultraviolet can change 6 to 8% in a 11-year solar cycle. And Lubitsky has shown, looking at actual data, statistically significant differences in temperatures from the stratosphere into the middle troposphere with the 11-year solar cycle, with the warmest temperatures at the max. And she attributes that to changes in the ultraviolet over the 11-year cycle. And Schindel, who works for Hansen at NASA, also developed a climate model and included ozone on ultraviolet, and he found that the stratospheric ozone changes that took place generated heat, and that penetrated down into the troposphere, in effect confirming Lubitsky's finding. We had a good example of that in 2001 and 2 when the sun had a second solar max that had very high solar flux, and high flux implies high ultraviolet, and you can see the result. The top picture is Lubitsky's correlation of solar flux and temperatures in the stratosphere, and you can see 0.7 in mid-latitudes. And the bottom is the actual anomalies during January and February of that year when solar flux was very high. A very strong warming in low and mid-latitudes, and cold air trapped in the polar regions. So certainly an indication of that effect. Tim Ball also referred to the aurora, and you see the aurora ring. You know, when we have a major bands. The aurora can be seen in the United States. And that color sky there's some warming involved. Now, we don't think it's way up there. We don't think of it as penetrating down into the atmosphere. But look what happens 11 to 14 days after a major solar event, a geomagnetic storm. You see that ring of warmth? And this is 500 millibars. It's like 18,000 feet. We see this frequently when we have a very strong solar event. And we actually use it in our forecasting. When we see a big solar event, we know 14 days from now, heights are going to be high across the northern United States. Regardless of what the computer models say. The sun attacks the low clouds, and low clouds have a cooling effect by reflecting energy. This is first proposed by Svensmark. He's been able to replicate it in the laboratory. And you can see it here, the inverse relationship of cosmic rays with solar sunspot numbers. When the sunspot number is low, the cosmic ray number in the bottom is high, and vice versa. And you can see the effect on cloudiness when at solar minimum, when there's more cosmic rays, there's more clouds. At solar max, when there's less cosmic rays, there's less clouds, and at solar min, more clouds. Okay, let's move to the oceans. There are multi-decadal cycles, and Bill Gray mentioned this. I'm glad he did. In the ocean, in both the Pacific and the Atlantic, that are being ignored. The IPCC admits that these are natural and are driven by long-term changes in the thermohaline circulation, which Bill will talk about tomorrow, and the corresponding large circulations in the Pacific, the Aleutian Low and the Pacific High. They admit only to regional effects. They don't believe that there's global impact. And the University of Washington, JPL, didn't discover this until the late 1990s. And they look at temperatures in the Pacific, that's the leading principal component of surface temperature anomalies, POED of 20. But you'll notice the horseshoe of warm around cold in the warm PDO phase and the opposite in the cool. But you'll also notice in the warm phase a tendency for warmth along the equator and cool in the cool phase. And in fact, the IPCC in their AR4 report included this diagram showing not only the bottom, which is the PDO cycle, the red being the warm phase and the blue the cold phase, but also showed what the sea surface temperatures were like in the warm phase. And you can see, in addition to that horseshoe of warm around cold in the North Pacific, you can see a tendency for warmth in the El Nino region. This would suggest more El Ninos in the positive phase. And if you look at the Wolters multivariate ENSO index, what do you find? You see the dashed line represents that great Pacific climate shift in '76. And red here is El Nino, and blue La Nina. You see after that shift, there's been predominantly El Ninos. And before that, when the Pacific was cold, predominantly La Ninas. La Ninas and El Ninos produce pretty much the opposite effect globally. El Ninos tend to produce more warmth, as we can see on the bottom right. La Nina is more cold. And you can see that change occurs very rapidly. When we went from the La Nina of the middle 90s to the super El Nino of 97, 98, it was a very large warming. Then it cooled into the La Ninas in the late 90s. And then we had 3 weak moderate El Ninos in the early 2000s. And then in January 2000, we were a moderate El Nino. And then suddenly, by the end of the year, a moderate to strong La Nina, leading to the largest 12-month period drop in history. So you can see how quickly temperatures respond to these Pacific changes. And you can see it when you look at the satellite-derived temperatures for the lower troposphere going back to 1979. All the El Ninos are warm spikes, and all the La Ninas are cold spikes. And this change, this big Pacific climate shift, produced more El Ninos. And remember, I have warm water off the Pacific coast. More El Ninos mean an Aleutian low that's stronger. And not surprisingly, a regime change took place in Alaska. This is Fairbanks, Anchorage, and Nome. You can see a 2-degree rise in temperature, almost instantaneous, and then levels off from there, a new change. And the same thing, by the way, John McLean has shown for Australia. with the shift of the PDO. You also see the extended cool period in the early 90s and 80s from the volcanic activity that I think Bob Balling talked about this morning. Notice that the activity, the amount of aerosols in the atmosphere has diminished. In fact, we're at the lowest level of the satellite era, according to Makiko Sato, right now. And if indeed the more stratospheric aerosols lead to more cooling because they reflect radiation from back into space, and as they fall out, they become condensation nuclei and lead to more cloudiness, as you see on the left. The opposite case, when the atmosphere is unusually clean, the stratosphere is unusually clean, should lead to warming. So what I did is I took years with the aerosols more than a half a standard deviation above on the left and below on the right, and you can see a dramatic difference. And so the low stratospheric aerosols may be contributing to the warming in the polar regions in recent years. Not the total factor, certainly. Again, this slide, the zero has slid to the south in this projection in this computer, but it shifted to the north. This is the Atlantic multi-decadal oscillation. It's a 70-year cycle. This goes back to 1850 to 2006, and you can see in the 1870s a peak, and again in the 1940s, 30s, 40s, and again in the 1990s. This is the mean ocean temperatures in the Atlantic from 0 to 70 degrees north. You see a very cyclical change in that. This is what the temperatures look like with correlated with the AMO on an annual basis. And you can see oranges and dark oranges are high correlations, 0.5 or greater. You can see statistically significant warmth occurs during the warm phase of the AMO. Well, I said if the PDO positive phase leads to more El Niños, which leads to global warming, and the positive AMO relates to general global warmth, then the sum of the two might be useful in identifying warm periods and when negative cold periods. And so I added the two together. Not a lot, but enough warming to be noticeable and have an effect. Now, Jennifer Francis in the GRL showed how the warming in the Arctic and melting was a result in part from warming in the Bering Sea, in the Atlantic side, that moves into the Siberian Arctic and melts the ice. And then there's a positive feedback of, once the ice is gone, of changed albedo. The National Snow and Ice Data Center mentions both. They mentioned Polyakov as a reference for the Atlantic, pulses of warm water that enters the Arctic from the Atlantic. They mentioned the Japanese JAMSTAC for the warm water entering Bering Sea. And they say many questions still remain to be answered, but those changes in ocean circulation may be important to the observed loss of Arctic sea ice. And you can see, here's the AMO, again shift the red line up to 0, but you'll notice that we really peaked the AMO, certainly in 98 shows up, but the 2004 and 5 were very warm. Those were those big hurricane years, and there was the Bering Sea was quite warm, and that warm water made its way into the Arctic. The Bering Sea is right at the bend there and at the bottom. And as the warm water also came in from the polar regions. And you can see 1995, when the Atlantic went warm, we started to descend in terms of Northern Sea ice anomaly. And we really bottomed out last winter, perhaps the result of that super warm period around 2004 and 5. And the Greenland, as was mentioned, was increasing in the interior in terms of its thickness, but decreasing along the edges with the warm Atlantic. Although the Greenland ice this year this winter was deeper. But looking at temperatures in Greenland, there was a negative correlation from the 1940s to the late 1990s with CO2. Temperatures declined, but peaked in the 1930s and 40s. It started warming in 1995 in the Atlantic. When the Atlantic started warming, it started warming in Greenland, but still hasn't yet reached the levels of the 30s or 40s and may not. Where will temperatures go from here? This is the plot of the Hadley and MSU temperatures. Well, this is a model forecast for the solar. This is a projection that suggests the next 2 cycles, 24 and 25, will be very quiet, very similar to those in the early 1800s. That means less solar brightness, less UV, less geomagnetic, less cosmic rays, more low clouds, thus cooling. And also, we've seen a rather significant, on the bottom here, drop off in that PDO. It went negative in the late 90s, it recovered to near 0, but has really declined again. So the PDO is cold. PDO cold means more La Niñas, so expect more of the kind of weather we saw this winter. If this persists, you can never be certain, but it's about time. It's about 30 years since the last change, and the PDO changes about every 25 to 30 years. The AMO nose has come off that peak in 2004 and 5 and has dropped off almost to 0 right now. So, in summary, temperatures have warmed, especially since 1979, but less than the global databases suggest due to contamination. Temperature changes are cyclical. The sun and ocean play an important role in that. And changes in these factors with the PDO and the sun point toward, if I were to make a forecast, a downturn in temperatures ahead.